So my name is Vasilos Karakassis. I'm a computer scientist here at CSCS. I work on several projects. Among them, one of them is OpenACC, or helping users, enabling their codes for running on our systems. And I'm going to give you a first overview of the GPU architecture. So here is the schedule. Well, it contains a bit, but this is the idea. So today we're going to talk, I'm going to give the first introduction to the GPU architecture. What is a GPU, how this processor look like, some specialties that it has against the CPUs. We're going to see all this stuff. And then before lunch, we're going to talk also on the short introduction and hands-on on getting into the system that will prepare you for the next day hands-on session. So just to get a bit, to familiarize yourself. After lunch, Mondays will take over and we'll introduce the OpenACC and Directive-based programming. I think that most of you have some experience with OpenMP. So this is like the OpenMP for GPUs or OpenMP-like directive programming for GPUs. Then we're going to talk a bit about profiling tools and debugging. We moved this a bit early in the schedule because then we start with a hands-on session. So you will learn some tools and how you can use them to analyze your code. On Tuesday is mainly a day with hands-on sessions. We moved all the hands-on session on Tuesday because on Wednesday we won't have available the system to run on. So we have several exercises that starting from basic things and a bit more advanced that I hope will help you to get your hands dirty and make the learning curve a bit less steep for getting into GPU programming and OpenACC. Finally, on Wednesday, which is a half day, we have a talk from Markus Wettstein from PGI, where he's going to present the advances in the OpenACC spec and the new features to come, and then Mondays will take over again with some more advanced topics about overlapping communication and computation and how you can do this on the GPU with OpenACC and OpenMP. So my talk today will have basically two parts. One is a bit introductory about GPUs in HPC and how we have come to this point through the years and why we see this trend. What are also the challenges for HPC applications and in the new era of the many-core. And then I will go a bit slightly deeper in the GPU architecture so that you can, so that I will show you the differences with the GPU, with the CPU, the key differences which have some implications also in how we program them and how we see some things happen differently. So you have all seen that there is a trend towards more parallelism on the node. So we have multi-core CPUs, and they were kind of introduced basically in 2000. I remember around 2006, we had the first Intel Core architecture where we had, it was a dual core, and then it was not even possible to imagine that on a single chip we will have like 18 cores or more. Like the KNL that they have 64 cores was like, okay, it's too much. But now there is a really trend towards that. And not only that, we have multiple thread context. So we have, for example, Broadwell, we have 18 core. It's an 18-core processor with 2 threads per core. And the power rate from IBM has 12 core by 8, which makes us like 96 hardware threads, basically CPUs. That's one thread. Then we have the so-called many cores. We used to have such processors. I mean, GPUs were around for years, but around 2008 and a bit before, people have started to exploit their computational power to do other stuff than graphics. And now we have the NVIDIA latest generation is the Pascal with 3,500 cores. So you can imagine that this is a huge number. And Intel also introduced the KNL architectures with 64 cores and 4 threads per core. So we have lots of node parallelism. And this is the trend. So this is how a node of Piz Daint looks like. So it has basically 2 parts. One, on the left-hand side, you can see the CPU. The CPU is, the green parts are the cores. So each core has, we have 12 cores. Each core has a private L2 cast and an L3 cast per core, and then we have the main memory, and on the right-hand side, you see the GPU. Every green small thing is a core. So you see that there is a lot of parallelism in there. And we're going to see how they communicate with each other. Let me just... OK. Oh. Sorry for that. So how we used to program in the past. I mean, lots of you have worked with MPI, probably most of you, if not all. And in the past, and we didn't have such parallelism. Basically, we had multiple nodes, different nodes were connected with network. And on a single node, we would have 1 or 2 processors. So MPI, the MPI programming model was the way to go. So we had the MPI model, most of you know, is each process has its own, it's completely different from the other, has its own memory, has its own virtual address space, and they just communicate with messages that they go either through the network or a common channel insert memory. How we would program back then, we split our problem in different chunks and in different sub-problems. Each node solved this sub-problem, communicated its result to the other nodes, and the other nodes went on with the subsequent steps. However, and despite that model, we always, in every new generation, we were having speed-ups. So we didn't have to care about how do we program. We just needed to make our program parallel. So make it MPI. OK, we had to take care about communication costs. That was important. OK, but on the on-node parallelism and on-node performance, I don't think that people actually cared about, because with every new generation of the GPU, of the CPUs, we had speed-ups. Why? Because we had an increase in clock frequencies. So we didn't have to care how the processor is inside, what happens inside, what's the pipeline, how do I make best use of the cast. That were mostly stuff that computer scientists love to do and never went into in the wider scientific community. However, today this is not the case, and probably some of you may have seen that figure before. So this shows the transistor density as it has evolved from the 1970s through today. And you can see that it doubles every year. And this is what we call the Moore's law. Gordon Moore was one of the founders of Intel, and in 1965 or 1969, I don't remember, he stated that the transistor density will double every 18 months. And that trend still continues today. So we have billions of transistors inside our chips. However, what is a bit strange is that Until 2004, 2005, we had an equal increase, exponential increase in the frequency. And suddenly, of the single core frequency. Suddenly at the 2004, I remember back then was the Intel NetBurst microarchitecture and the Pentium Force. And if some of you remember, there was back then the 3.8 gigahertz or something like that. It was very, very fast processor. So what has happened? I mean, first of all, before going to that, what the bigger transistor density could give us? Of course, we had lower latencies inside the processor, so we could make the processors faster, the circuits were faster, but also we could increase, we could have deeper pipelines. Deeper pipelines means that, has anybody of you heard about the pipeline? What is the processor pipeline? So the processor pipeline is when you execute an instruction, the instruction is split in several small phases. And there is dedicated hardware that executes each phase. Why is this important? Because you fetch one instruction, it goes through the pipeline. When the first instruction goes to the next stage, I can pick up a next one. And then I have a high throughput. So instead of having to wait like 10 cycles for instruction to finish, I just wait the first time 10 cycles, and then I wait one cycle every time until I produce a new instruction. So this is at the core of each microprocessor. So having higher densities has gave us the opportunity to have deeper pipelines. For example, the NetBurst microarchitecture has like 30 stages. So each instruction passed through 30 stages. That has the good thing that we could increase the frequency so much, but had other negative aspects as well. But I'm not going to go through this now. But what happened in 2004 was that the power density of a single chip has increased very, very large. It was around 100, it was approaching the limit of 100 watts per square centimeter. And just to make a comparison, the power density of a nuclear reactor is 130 or 140. So engineers at this point understood that this can't go on. We can still manufacture denser microchips, but we cannot increase the frequency. So, because the key problem with the frequency is that the power consumption grows with the cube of the frequency. That's what we call the power wall. So you cannot increase the frequency, you will hit the power wall, and that you cannot go any further. And that's because most of you might know the equation power equals C by V squared, where the V is the voltage. So in order to increase the frequency, we had to keep up high voltages. So that makes it proportional to the cube of frequency. And that's a problem. So similarly, the single core floating point performance is not keeping up. Why? Because that's because the frequency is going down. So how do we increase performance then? We cannot increase the clock speed anymore. So engineers, processor architects went down to and thought about different ways and using the more transistors they could build, and they used them to build more processor contexts. These are either cores or hyperthreads, or multiple threads that they share the same resources inside the core. Or there is also instruction-level parallelism. What that means, the processor can execute multiple instructions at the same time, and multiple instructions are on the fly at the same time. And the other thing that's also now becoming a trend, it's the so-called vectorization. With a single instruction operates on multiple data. So with a single instruction, you operate like, you do 4 real additions, 4 real floating point multiplications. So this basically increases parallelism without increasing the frequency. What that means, we don't increase the power envelope of our processor, but we actually increase its performance. So, and the third is design the processor such that we don't have to stall, or I mean the application that we write. What is a stall? A stall is when the processor cannot proceed basically. So it cannot fetch another instruction to run because it's waiting for memory accesses, or there are dependencies between instructions, or there is a branch prediction. So what does branch prediction mean? Control flow is everywhere in our programs. So if you have a tight loop and then somewhere inside you do an if, and that if can be taken, I mean, that is a branch. This branch can be taken or not taken. The processor cannot know. So it keeps up a history, and based on that history, it predicts and says, okay, I predict that the branch will always be taken. So it's continuous fetches to fetch instructions, and but if eventually the branch isn't taken, then he has to flush all those instructions. So these are the 3 ways, basically, that we can increase. The performance was increased in the architecture level, but also the applications must be aware of those advancements. So as I said before, clock frequency won't increase. Why? Because of the Powerwall problem. So you can see that even a 4-core Haswell processor at 3.5 gigahertz has the same power consumption as a 12-core Haswell at 2.6 gigahertz. And I bet that on 12-core Haswell you can get much more performance than a 4-core Haswell. And you can also see that the GPUs, the frequency of the GPUs are very, very low. And indeed, they're quite power efficient, energy efficient devices. Of course, I mean, it's not completely fair to compare a single core of the GPU against a full-blown CPU core. So all this discussion is about that parallelism will eventually increase, and there's no sign that it's going to stop for the moment. So we have several dimensions of parallelism. One, as I said, is the number of threads per core. You see that we have, not only we have multiple cores, now each core has multiple threads. What's the concept behind this? Basically, the resources of the core, they are shared among different threads. So when an instruction goes in, then the core decides automatically which instructions are ready and schedules them to run. And you see that Haswell has 2 threads per core, KNL has increases that 4 threads, and IBM Power 8 goes to 8 threads per core. We have also large vector lanes. We have parallelism in another direction. So this means that with a single instruction, we do multiple. We can do multiple operations. We have 256 bits, 512 bits. So you see that there is a trend to increase parallelism in every possible direction. So enough about these general concepts of parallel architecture, but let's see what's the difference between CPUs and GPUs. So on the right there is a picture, it's an old picture from NVIDIA, where you can see how basically the die area of the chip is divided in CPUs versus GPUs. So for the CPU, you see that the majority of the die area is occupied by the caches. And the cores are relatively small, and you have lots of die area dedicated to control logic. Why this is important? Because CPU were designed not for throughput computing, not for basically scientific computing. They have to deal with lots of heterogeneous tasks. So it's not only our kind of applications that we are used to. There are also applications with databases. There are also applications, web applications that the CPU should be good at. So for those applications, it is crucial that most of the time they suffer from latency. I mean, they might have access patterns to the memory that they're not optimal. So you have to have large caches to be able to provide performance. And you may have not regular control flow, so you have to have a good logic for predicting. So that's why you have so much logic dedicated to cache and control. On the other hand, the GPUs are a different thing. So caches are minimal. Control logic is minimal. And you have plenty of small, of very simple, lightweight cores. And that's also a difference of the workloads that each architecture is designed for. The GPUs are designed for throughput computation. So, so you want lots of operations to happen at the same time. You need lots of parallelism. And also, I mean, the way you deal with memory latency is different. The CPUs deal with memory latency, with misses and stuff, with large caches. Whenever you miss, you put it in a cache that you do not miss the next time. For the GPUs, there is a difference. You don't have so large caches, but what do you have? You have plenty of threads, of cores that they can run. So you need to have a quick way that whenever a thread here stalls, then because it waits from its data to come from memory, then the hardware should be able to schedule another set of threads to take its place, so that the overall computation will eventually go through, and then the latency, this wide gap will be covered by useful computation. And you can also see here the black box, which is the context switch. In GPUs, you don't see that. What is context switch? Anybody knows what is context switch? So context switch it's something that's performed by the operating system. So I mean, one could say, okay, you tell me that you have thousands of threads that can run on parallel on the GPU, but so it does happen also on CPU. I mean, if you see what's going on the CPU, you have hundreds of threads, but we have only a bunch of processors. So what happens is the operating system stores, I mean, evicts whatever the registers of the current process that it's running, evicts them, stores them somewhere in memory, brings in the register of the next process and goes on. So this is called context switch. In GPUs, we don't have such a thing, because this is very costly. And we're going to see how the hardware enables that. You don't want to intervene, outside processes to intervene, or the kernel or whatever. You just put it computation there and let it go with computing ready stuff. So the problem is that you see that in the past we didn't care about what's on computer architecture, basically. We're writing our code, and then we expected the next generation to come, give us more frequency, and boom, we had performance. Now, that's not the case. So suddenly, the applications are not prepared for this on-core parallelism. And there are several dimensions to this. So first of all, the applications are not, I mean, we should start thinking a bit differently. So we should start thinking for extracting parallels for the application. We should start thinking in parallel somehow. And we should design also our application as such. Also, we need different programming models. Okay, in the past, we had the MPI model, and we had also the shared memory model, but now we should also think of, we have new dimensions. For example, the GPUs are called processors. We should deal with that. Then we need to extract some in parallel. So ideally, we should not think of, okay, where do I place each task? But we should think of ways that we just create parallelism and design our application in parallel using probably task-based models that we spawn threads, and then they run on the hardware, and they make efficient use of it. Of course, we need new algorithms, because traditional algorithms may have been designed and tuned for the old programming models. Now we have so much parallelism that new algorithms, that the older algorithms are becoming obsolete. So, and of course, I think most of us have come into the case that we inherited some code from older generations that it was doing good physics, good biology, it was producing results, but now, I mean, we still need to get the same quality of results, but we need to make use of the new architectures. And unfortunately, this old code usually has to be rewritten or refactored. And that's the purpose also of these directives and directive-based programming, because it makes this task less tedious. And as a result, the compute nodes at the supercomputing centers are usually underutilized, in the sense that, has anybody of you ever checked how close to the peak performance of the node runs its application? Most of the time it will be like 10%, or if you get a bit more, then you're good enough. So basically, we're underutilizing the allocation. So there is a room that we can get more of the allocation, which basically means less node hours, more environmental friendly, or more useful science in the same time slot. Okay. So now I'm going to go in the second part. If you have any questions, you can stop me anytime. So before I go on. So the second part is we're going to see some more, in a bit more detail, the GPU architecture. Here is what the P100 GPUs here that we have at CSCS look like. So again, the small green things are the cores. You cannot even see them. There's so many. And you see also some group of them. So it's like we call them multiprocessor. We're going to see it in a separate slide exactly how they look like. So the GPU is a collection of these multiprocessors, and each of those multiprocessors has a series of cores inside it. You can see that there is also a large, the blue in the middle, there is an L2 cache shared among all the cores. And you can see the memory controllers on the right and on the left. And the green boxes on the bottom are so-called the NV links. So these are high-performance links that you can basically link multiple GPUs together. So now you can see that we have another direction of parallelism. We don't have just parallelism across nodes, but we may have parallelism on the same node among different GPUs. So multiple dimensions. And on top is the interface, because it's the PCI Express interface, because those cards are connected to the rest of the host, to the rest of the node through a PCI Express bus. And then you can have a network of, as I said, of GPUs. So let's see how this I think it's simultaneous multiprocessor or something like that. Symmetric multiprocessor, yeah. Symmetric multiprocessor architecture. This is not from the Pascal. I just picked up the previous generation because it fitted better on the page, but the idea is the same. So the GPU comprises multiple such blocks of SM processors. So what is an SM processor? SM processor is consists of several multiple lightweight single-threaded cores. So it's 64 on the Pascal architecture. So each of those cores are very, very simple. So it doesn't have any of these heavyweight logic of branching prediction, out-of-order execution, and that stuff that the normal CPUs have. And they use lots of energy for that. They're simple, lightweight cores. What is key here is that those cores are not independent with each other. So they operate in bundles of cores or threads, so that we call them warps. And each warp consists of 32 threads or cores. So this group of 32 cores, at every cycle, they execute the same instruction. So, and then they proceed in bunches. So the first, for example, we have a load here. The first 32 will execute the load. Then we will execute the next load, the next operation, and so on. Now we have, what's important, in every SM there is a very, very large register file. Do you know how many register a normal CPU has? Have you any idea on which order? It's in the order of 30, 40. If you count also all the different SIMD registers, I don't think it's more than 60 or whatever. Here we have, and I may be saying a lot. Here you have a 256 kilobyte. So if you divide this by 10, it will give you like 32 or 64 key registers. So there are lots of registers. So you might say, why I need so many registers? Now, go back to what I said in the previous part, that in order to run something, you have to have your state somewhere. And on the CPU, you have your registers somewhere, and in order to get to run another process, you swap them out, in the memory, and then you bring on the new registers. Here, you can't do that, because then you have to do a real context switch, and you don't want that. So for this reason, every little core here should have its own set of registers stored physically on the SM. That's why there is this very large register file. So each of these 64 cores, for example, if one core requires like 10 registers, then I would need 640 registers to run 64 cores at the same time. But again, we're not at the level of 256K kilobyte register, but that's another issue. We're going to see it in the next slides. And then there is, on top, there are several warp schedulers. These are basically take care of dispatching the warps for execution. So there is imagine like a queue of warps that are ready for execution, and this scheduler picks up the next one, that is the next group of 32 threads to run, and puts it on the multiprocessor to run. Then if this warp does a memory load, and it has to wait for memory, then the warp scheduler picks up the next ready warp to run and puts it on the execution. So this is how the memory latency is covered. There is no such thing as large caches or that we have on the CPU. So you have to have lots of threads available to run so as to cover the latency. And then there is, here at the bottom, the blue things they're a level 1 shared memory that can be either user managed or hardware managed. This means that the user has control on what to put, or can potentially have control on what to put, on what to cache. That's a notion that we don't have on the CPUs, right? On the CPUs, caches are kind of transparent. We just fill them from their effect. But here, the programmer is able to put specific like arrays or parts that they are used in the cache, and he is responsible of doing so. So let's say a bit about the execution model. So this is what we call, the GPUs are programmed in a host-directed execution. This means that they don't have an operating system running on them. So it's not possible that it's not like a normal processor. So you have to control them somehow externally. So you need two parts. You have the host, which is the CPU, and the device, which is the GPU. So the CPU sets up the kernels, sets up the applications and what should be run on the GPU, and we call the codes that they run on the GPU, the functions that they run on the GPU, we call them kernels. So the CPU sets them up, sets up the launch, and finally launches them on the GPU. And also, CPU has to manage the memory of the GPU. So it can allocate memory on the GPU, should copy the memory from the host, the GPU, so do all the preparatory stuff in order to be able to run. And then launch the kernel, and there you go. However, even I think from CUDA 6 and the Kepler architecture, there is also what we call the unified memory. That's kind of for those that they used to program with the GPUs from the early days, I remember lots of papers dealing with that things in computer science about how we can virtualize the space, the address space between CPU and GPU. And that was a very nice feature because you don't have to care about where is my pointer, or is it on GPU or is it on CPU? If it's on CPU and I access it from the GPU, I don't want to crash. I want to bring it to the GPU automatically, and I don't care. That would be the ideal. In the past, you couldn't do that. So there is this thing already supported in the Kepler, but in the Kepler architecture, which was the previous generation, this wasn't so efficient because it was completely handled by the runtime. So the CUDA runtime, so you had to allocate specifically in a specific place of memory, and then the runtime could take care this special pointer that do the translation stuff. Today, this is quite efficient with the Pascal because the driver, and there is hardware on the GPU that handles page faults. So when you, for example, you can do normal mallocs, and when you access a page that's not on the GPU, then this page will be transferred to the GPU. And it really helps you completely like erases the data management. So although this may be needed in more advanced cases, but this is quite a nice feature. So let's see how this huge parallelism of the CPU, of the GPU is managed. So as I said, an application launches kernels, which is basically the code that executes on the GPU. And now each kernel comprises several blocks of threads. So when you write a kernel, you should think a bit in parallel. For example, you don't have like an iteration or a for loop could be split. I mean, each iteration could be a different thread doing work. And so you end up having thousands of threads. Now, those threads are organized in blocks. So a block can have like 256, I think, maximum number, or 1024 maximum number of threads. I don't remember the exact numbers, but they are organized in blocks of threads. Now, each of those blocks runs on a single SM, on a single multiprocessor that I showed you before. So now, it is possible that multiple blocks can run on the same SM. And why is that needed? Because, as I said to you, there is so large resources about register files, and we want to have lots of warps ready to run in order to cover latencies. We don't have any caches or any large caches. So the more threads we have, the more likely it is that we can have good performance. So there are several things that can be. There are three factors that control how many blocks can be accommodated in a single SM. So, are there enough registers? If, for example, if my kernel takes a huge number of registers and my block, I have 256 threads per block, then probably I could just put a single block, but then I wouldn't utilize completely the device. Is there enough shared memory? If, for example, my kernel fills up the memory or gets all these shared memory that I showed you that's per SM, then I basically block the whole SM. So these things, the programmer of a GPU has to have in mind. And of course, there are also hardware limits. Now each block is kind of organized in, as I said, bunches of 32 threads that we call warps. These are the basic execution unit. So if you have if you have a block with 128 threads, then you will have like how many warps? 2, 4, 8 warps. So every time one full warp will be selected to run, and then the next one, and then the next one. So you should remember that this goes by 32. So this model might seem a bit complex. Well, at least it's a bit different from what we have learned from the GPUs, and it has some implications as well. So as I said, and I have accentuated before, is that we need lots of parallelism. We need to have lots of available warps. So you can't go with like 10 threads. I mean, if you on the CPU, if you have an application with 10 threads and scales, or 12 or 32, wow, that's pretty good. If you go with 32 threads on the GPU, that's completely underutilized. You have to give thousands of threads, and then let the hardware pick up the next bunch so as to cover the latency and keep the GPUs busy. It's a different kind of architecture. Another application that's not so obvious, but it is quite important, you cannot do global synchronization across all your threads. That's something that we are used to it, right? We do an MPI barrier or a no-MP barrier across all our threads. That's not possible on the CPU. And there are technical reasons about that. I mean, apart from the fact that there's no coherency across our coherence protocol across the different multiprocessors, the other problem is that not all the blocks of the applications run of your kernel run at the same time. For example, if say you launch a kernel, you request like 4,000 threads, and that makes 5 or 6 blocks, but only 3 of them can be accommodated on the SM, for example. Then those 3 first blocks will run into completion, and then the next 2 will be scheduled to run. So why this is needed? I mean, it might sound a bit strange, but this is the requirement to have this very, 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 very fast context switch. Because if I had to kick out a block, bring the other one, then I had to store somewhere the registers, bring the other registers in, do all these things that the normal CPU does. And you don't want that. So you have, every core has all its resources on DSM. So this ensures that there is lightning fast context switch from one warp to the other. But this has this downside. You cannot globally synchronize in a reliable way. How you can synchronize is you launch another kernel. So this is another dimension. You should look at your application a bit differently. I can split the different phases of the application as different parts to run on the GPU. So, and this, historically, this also comes from the GPUs, what they were serving before. They were serving graphics, right? So graphics process is a really pipelined process. You have one phase, for example, does the geometry, one does the shader thing, one does the other, and the result of each phase, the output of each phase was the input of the other one. You didn't have all these dependence, so this is the idea. So you have to structure a bit differently your application. Another implication of the execution model is that I have said before that everything happens in bunches of 32 threads, but you have the opportunity that some of those threads may want to execute, because of your application, may want to execute a different path. So, for example, the first 12 threads or cores needs to get to one path, and the rest 18 to get another one. The rest 20, sorry. So what happens? I said that the hardware executes always the same instruction in these 32 threads. So the hardware will just do, okay, I will execute both branches. I will check the first branch and disabling the 20, masking out the 20 warps, and then I will execute the other branch, masking out the other part. So basically, it's like this is called, in the terminology of the GPU, is called divergent warp. And although this was initially, when you start to program with GPUs, or in the past, well, that's a feature that we're not used to it. But now, this problem, that even the CPUs are getting wider vector lanes, this problem comes again in. Because you can view the GPU as a very, very wide SIMD processor. So, for example, if you go on the CPU and you have a 512, you have a register with 8 floats, and for some reason you want to do some operations on the first 4 and some other operation on the rest of the 4. Then again, you have the notion of divergency, because you should mask out the half of them in the first part and then mask out the second part. So that's the same idea, but it's different terminology. But you see that this terminology that we have, this concept, we have very wide registers, comes up again. So yes.
I want to ask, if I want to do synchronization, then very rarely, every once in a while, then I launch a kernel and wait until it stops.
Yes.
And then I do.
Yes, and then you launch another kernel. So now I'm going to talk a bit about the memory model, and then we can go for a break. So, so we have different levels of memory on the GPU. We have the so-called global memory, which is on the Pascal GPUs. In the past, it used to be GDDR5. In the new Pascal, it's the new technology of high bandwidth memory that delivers very high bandwidth. For example, you see here it's 558 gigabytes per second, so this is huge. And this is accessible from all SMs. It's the global memory of the GPU. So this is usually the memory where you put your arrays in, and it's your workspace, basically. Then on each SM, you have, I showed you before, what is called shared memory or level 1 cache. It can be used as both. Either you can manage it or let the hardware manage it for you. Like so as to behave like a normal cache on the CPU, but you can also use it yourself, allocating arrays or parts of arrays inside there. And then this is accessible, is shared within an SM, and this is accessible. It's very fast, so ideally it has 1 cycle access latency. This is organized, just to visualize it, it's organized in bunks, like most of the memories are, basically. So if you don't have bunk conflicts is when 2 or more threads request an address that resides in the same bunk. So this means that we have to serialize. So the worst case will be 32 cycles latency when each thread of this warp, of this group of threads, access the same shared memory location, then all of them will be serialized. That's an implication. That's 32 cycles. That's a lot. And ideally, if they access different addresses or contiguous addresses, then you have the best case. Another thing I didn't tell before, but it's also related here, is that there is only synchronization. I don't know if in the slide could be on, but I'm not sure. You can only synchronize the threads within a block, within an SM. Now, another important feature of this memory is there is no cache coherency between the different shared memories or level 1 caches, whatever you like, between the different SEMs. What's happened on the CPUs? For example, if we have several cores or different CPUs, and I write something in my cache, which is on one node, and then I read something from the other cache on the other node, at the same location, and I get the updated value. How that's possible? There is a protocol running on the hardware that invalidates, for example, the copies that the other processors may have, and they all request the updated value. When they need to load an address, they just get the updated value, and this is taken care of by a protocol that's called coherency protocol. This is more primitive here. So the user should be responsible for synchronizing between the threads and making sure that before accessing, for example, you write something on the shared memory, and the programmer should be responsible for synchronizing the threads and making sure that all the threads have gone through this point so that we know that everything is written on the shared memory so that we can safely proceed. So this is a bit different. So the programmer must be a bit more aware. And finally, there's also these level 2 caches that you don't see is shared across all the SEMs. It is hardware managed. So final slide for this session is how do you program the GPUs? So one way is to go with CUDA. CUDA is basically a set of C++ extensions, and it's low level. If all these things about the architecture have sounded to you a bit complicated, and I bet they did, then in order to go CUDA, you have to understand the architecture and also think differently on the way you structure your code. You won't see any more loops because loops are kind of degenerated into loop iterations generated different threads, different things to execute in kernels. All these things are, if you write CUDA, you have to understand very well the programming model and the GPU architecture. And of course, it's more explicit. You have to write more code because you have control on everything, but on the other hand, you may not want to do that. Then is the purpose of this course is you can go with using directives. And then it's much easier to write, much more productive, and it's high level, so you still don't have to take this leap to understand deeply the GPU architecture, the programming model. You just have your loops, you say, you will see it, and it's more natural on the way we have been used to thinking and write parallel programs. So after lunch, Mondes will go on and will show you the GPUs. So now let's, if you don't have any, I mean, do you have any questions? Okay, so let's have a coffee break now. And after the break, JG and I were going to do a first hands-on on a first presentation of the programming environment so that you can log in and just familiarize a bit for tomorrow's exercises. Yes, please.
Are these presentation available as
What?
the
The slides, yes. I will upload them. Yeah.
Okay.
I will upload them. Will be available. I will let you know. Yes, please.
Yeah, what different hardware vendors actually? Now you talked all about NVIDIA GPUs and that architecture. How about the AMD GPUs? I mean, of course, CUDA can't deal with that. They need OpenCL, but how about OpenACC and OpenMP? Can you repeat the question?
So yes, our friend here asked what. These are all about the NVIDIA architecture, how it looks like with AMD ATI cards. It's very similar, I would say. So I have not programmed with ATI. I've seen a bit the APIs that they had also a similar CUDA-like programming model and programming environment. The idea is the same. And if you see also OpenCL, which is kind of the umbrella for all of these, they have the same concepts. It's just the terminology different. So you have like workers, you have, but the idea is the same. And because they have the same, they come from the same roots, because they were graphics cards, were designed for something else. And at some point we said, wow, we have so much computing power, why not use it in our problems? So the idea is the same.
But can I then use OpenACC and OpenMP to address AMD GPUs?
That depends on, I don't think a compiler, so it's a matter of compiler, I think, so to have a backend to support that. But as far as I know, they are all based on CUDA. So basically, they emit CUDA code.
So perhaps they are not compatible. So perhaps there is no ACC support for AMD devices.
Yeah, no, they're not. No, it's not. So if for non-NVIDIA things, I think you should go OpenCL probably. And then you get both.
You can also use the OpenMP as a target directive to port your code there. I guess if the other architectures become more popular, also the compiler will support that. You can also use it. I mean, that's the advantage of using these directives, that you not focus on specific hardware, but that you have a more general point of view to port it to different hardware also.
Okay. So let's have a coffee break.